I want to go over the class question slides in a video with you because I wasn't here when you had this class, just to make sure you get all this stuff figured out. So I suggest that you read the slide, think about it, arrive at an answer, and then I should say pause the slide, read it, think about it, come up with an answer, and then unpause it so you can see what I have to say about it. So a couple of things is we can just say if we want to phi is kq over r. So the smaller r is the bigger phi, and that would lead us to point A is closer. We'd have an A for at which point in space is the electric potential greater. You can also think of it conceptually. So we get some charged particle here, and our electric potential is 0 at infinity. And if we imagine bringing in a positive test charge, then it's got a certain amount of potential energy. At infinity, that amount of potential energy is 0. As we bring it in, we do more and more work on it, something like lifting a book near the surface of the earth. We do work, we're forcing it upward away from the earth. We have to do positive work on it in order to lift it up high. Same thing here. In order to move it closer and closer to the positively charged particle, we have to do more and more work on a positive test charge, and that means the potential energy of the system is getting bigger and bigger. And I said we're going to assign that to the positive test charge itself. So the closer we move the positive test charge to our fixed source charge, the more potential energy it has. We do more work on it. It's kind of like lifting it up, getting it closer. We push it closer and closer. We're storing energy, and the closer we get it, the more energy we have stored. And then the more energy a positive test charge has at a point in space, the greater the value of the electric potential at that point in space, the potential energy per charge. You know, for our test charge, we would just have to divide the potential energy divided by the charge of the test charge to get the electric potential energy per charge at that location in space. In other words, to get the electric potential. So the closer we get it, the more work we had to do, the more energy we stored, and therefore the greater the electric potential. So once again, we arrive at the case point A is closer. We would have to do more work to bring in the positive test charge, hence we'd be storing more energy, and hence the potential energy per charge is greater at the point in space that's closer, and hence the electric potential is greater at the point that's closer. Alright, probably too much said on that one. A negatively charged particle. Go ahead and read this one. So I guess the idea would be, if we could use one of the constant acceleration equations, is we'd use the force is equal to kq. Well, k times E, the force is k times E, and the electric field at the point in space is kq over r squared, where the positively charged particle is the q. And we could also look at it just using Coulomb's law and say the force is k times q1, q2 over r squared. Now, and then the idea would be, once you got the force, draw a free body diagram, apply F is equal to ma to get the acceleration, and then use the acceleration in a constant acceleration equation to find the answer to the question. Released from rest. So the problem with that is that the force is not constant. As the negatively charged particle gets closer and closer to the positively charged particle, the force gets greater and greater. So the force is not constant, and therefore the acceleration is not constant. And you can't use the constant acceleration equations when the acceleration is not constant. So no, that would definitely not work. I come back to this one. I want to see if I got a follow-up question on it, but we definitely can't use it because the acceleration is not constant. Alright, let's move on to the next one. Alright, I do want to go back to this one. I don't have a follow-up question. So how would you do it? Well, I would use conservation of energy. There's the point you're asked when it arrives at a point. So you need to know how far the closer point is to the positively charged particle. You need to know how far the release point is away from the positively charged particle, and then you can say the total energy in the before picture is equal to the total energy in the after. In the before, it's a combination of you can say it's K plus U, and the U is the electrical potential energy, but the K is 0 there, and you would say that's equal to total energy in the after picture, K prime plus U prime. The U prime is different. The K prime is not 0, it's 1/2 mv squared, and we can use that to solve for it. Now, presumably, if the total energy is the same, which is what we're saying, and now it's got both kinetic energy and potential energy, the potential energy must be lower than what it was before. And indeed, the potential energy for the case of a negatively charged particle is its charge, a negative value, times the electric potential at the point in space at which it's at, which will be a positive value because of the the fixed positive test charge produces an electric potential that's kq over r, so that'll be positive. So in other words, the potential energy is negative, and because of that r in the denominator, the closer the negatively charged particle is to the positively charged particle, the more negative it is. It's a greater magnitude, but it's negative, and so yeah, it does have a lower potential energy. So the total energy being the same is consistent with the idea there that as it acquires kinetic energy, it gets its potential energy gets more and more negative, such that the total is the same as what it was to start with. Alright, let's draw a picture of this one. We got a coordinate system. Try it. An x-axis over there. Y-axis up this way. You got a positively charged particle here. Let's call that, I'll write a symbol down that makes it look more like a positively charged particle. So positive there, and a negatively charged particle 12 centimeters to the right of that. And we're looking for places where the electric potential is 0. Now the electric potential is going to be kq1 over r plus kq2 over r, where this one is negative, and this will be, I'll call it R2 and this R1. So if I pick some point P in space, the distance to number 1 is my R1. The distance to the negatively charged particle, the one that's got charge of Q2, is my R2. Now one of these terms is positive and the other is negative, and I need for them to add up to 0. I'm looking for places where they add up to 0, and they on this plane. So on the plane of the page. Now the fact that one is positive, the other negative, means algebraically, if they're of the same magnitude, they can add up to 0. And one of the big differences here when we're talking about the electric potential compared to the electric field is we're not talking about a vector. So there's no direction associated. It's just numbers with units, values with units here, and one's positive and one's negative. So we just need them to be the same size. And the point is there's going to be an infinite number of places where they're the same size. If Q1 and Q2 both have the same magnitude of charge, it'll be an infinite plane or infinite line of points everywhere on this line. Everywhere on that line, any point on that line, the distance from 1 to point P is the same as the distance from 2 to point P. Now, suppose 2, however, is of smaller magnitude than 1. So we got a big positive charge and a relatively small negative charge. Then the points where these two add up to 0 aren't going to form a plane, but it'll be a curve, something like this. Somewhere in here, in this region over here, if Q2 is smaller, I can make up for the fact that it's smaller by getting closer to it. So if the R's were the same as each other, then the answer would come out positive. So I make R2 smaller than R1 by just the right amount, somewhere over in this region, and I'll find some points where that's the case. So there's going to be an infinite number of points. This curve through space, any point on that curve corresponds to a point. I mean, I've made up the curve, but let the curve be that locus of points that makes it so that this adds up to 0. In other words, we're hunting for things where phi is equal to 0. That's going to produce a relationship between the R's, which I can express if I take one over to the other side and then solve for it. I think I'll have, let's see if I can get this. I'm going to cross multiply, so I got R2. I'll multiply both sides by R2. I'm going to solve for R2. Q2 over minus Q2 over Q1 times R1. That's all we're looking for. All the points for which this is true. That the negative of the ratio of the charges is equal to the corresponding ratio of the distances. And I want to think for just a second, make sure I get that right. R2 over R1 has got to be equal to the negative of Q2 over Q1. And yeah. So that can be met at an infinite set of points, as long as we get this R2 is this factor times R1, then the condition is met. So an infinite set of points at which V is equal to 0. This curve will actually be a closed curve because there will be a point over here, for instance, to the right, if on the x-axis, if the magnitude of Q2 is less than the magnitude of Q1. If it's the other way, it'll be a closed curve over on this side, surrounding the charged particle number 1. So only at one point, no good. Only at one point, only at one point. At 2 points, now an infinite number of points. That's what we got. Alright, let's move on to the next one. Consider 2 positively charged particles. I'll let you read it. So this is a big deal. This question, even though it comes under the electric potential, is a question about the electric field. Here, where's the electric potential? 0, but in our next one, any points besides an infinity at which the electric field is 0. And we're looking at 2 positively charged particles plus are there any points in space? Yeah, anywhere in here. It's going to be closer to the charged particle that's got the smaller value of charge. But anywhere in here, if that's number 1, this is number 2. E1 is away from that one. E2 is away from charged particle number 2. And somewhere in there, you're going to find a point. That's the E2. This is the E1. You're going to find a point where they cancel each other out. So they're in opposite directions, so they can conceivably cancel each other out. Look at the E. This would be E1. This is E2. So these two are in opposite directions, so they can cancel each other out. It's just going to be on the line there. So anywhere off the line, you can't get cancellation. Anywhere to the right, both E1 and E2 would be to the right, so you can't get cancellation. Anywhere to the left, on the line passing through both particles, you get both E1 and E2 are leftward, so they can't cancel each other out. But in between them, you can. So are there any? Yeah, those at infinity they mean an infinite distance away from the pair of particles. And sure, there's a place. So that would be a yes. And then we move on to the next one. And here the answer is no. The big difference, once again, is that when we're talking electric potential, we're looking at a scalar. So we're looking for points in space where the two contributions add up to 0. But any point in space you pick, both terms are positive. So you're adding two positive numbers, you can't get 0. The only way you could ever get 0 is if both the numbers are 0, if they're non-negative, and that only happens at infinity. And they said besides, right in here it says besides at infinity. So the answer is no. All right. Is this a trick question? I start out by asking. Go ahead and read it, please. I'm hoping it doesn't seem like a trick question. It's just checking to see whether whether the electric potential is a scalar or a vector. It's a scalar. Scalars don't have any direction. The electric potential doesn't have any direction, and so none of the above is the correct answer. We don't have that option in there. They actually give two specific directions. So take a read of this one, pause the video and read. Oh, here's that follow-up question about that one. Where can you use the constant acceleration equations? And the answer there was no. And I said, well, then what would you use? And you would have to use conservation of energy. It would be very wise to use conservation of energy. You could do with it an integral method where you allowed for the variation of the acceleration, but much easier to do it this way. That is conservation of energy. Oops, circled the wrong one. So let's get that fixed up. There we go. Conservation of energy. So the idea is find the total energy at the release point, write an expression for it, find the total energy at the new point that's closer to the fixed charge, set the two equal to each other. If it was released from rest, then the original kinetic energy is 0, and at the new point it's going to have a greater kinetic energy. If you released a positively charged particle from near a fixed charge, or a fixed positive charge, or a negatively charged particle near a fixed positive charge, then in the after picture the object is going to be closer to the fixed charge. But if the two charges are like charges, both positive or both negative, then it'll be further away. And enough said about that. Yeah, I'd use Newton's second law to get the acceleration at a given point in space. Now, that idea that you can't use Newton's second law plus constant acceleration in order to find the speed of the particle that was released from rest at one location and is now at another location. That doesn't mean that at every point along the way you can't say what the acceleration is. It's just that the acceleration is not the same for all the points along the way. That is, it varies, but yeah, we could find the acceleration just by f is equal to k q over r squared, or f is equal to k times e, and where e is kq over r squared, and we've got it. We can get the acceleration, we just can't pretend that it's constant as the particle moves along. But the acceleration at one point in space, yeah, that's no problem. And we would use f is equal to ma, draw a free body diagram of it, determine what the force is on it from q over r squared, or from ke, with e being kq over r squared, and the final q being the charge of the source charge. But there's no problem in applying Newton's second law. Draw a free body diagram and apply it. Free body diagram. You get it wrong. So what happens is people get so used to using E is equal to kq over r squared that they forget that when it's time to calculate the electric potential, it's the phi is given as kq over r, just plain r. I'm one of those people that made that mistake myself, but I'll try to never make it again, is the point, and this slide can help remind one. You get it wrong. So that would be B. Not sure I ever put one down. A free body diagram is needed. Alright, let's call it a video for lecture 6.